Hi guys, it's your science teacher and welcome back to another video. This time I'm going to go through the whole of the unit which is titled the Earth's Resources. So without further ado, let's get started with today's video. Now the Earth's resources is all about where we get our materials from, how we dispose of their materials, and also the impact that all of this can have on the environment. So the first thing we're going to look at is two different types of resource: synthetic resources and natural resources. Let's take, for example, these two bags down here. Now over here I have a paper bag, which is classed as natural, and over here I have a plastic bag, which is classed as synthetic material. Now the reason why the paper bag is natural is because it's come from trees, and trees obviously come from the ground, they're planted, and this comes with its advantages. These natural materials are often renewable. This basically means that if I want some more paper, I can just grow more trees. It also has the advantage of the fact that these natural resources are often biodegradable, being the fact that they come from nature. They often decompose quite well. So you might be saying, well, why do we even have synthetics? Well, this is because natural materials often do have some key disadvantages as well. For example, if we're using trees to make paper bags, this requires lots of land. It's the same with cotton. If you are growing cotton for a cotton farm, it's going to require a lot of land which could be used for other things. Also, it can be quite an expensive material to process, so we have found alternatives, and this is where synthetic materials come in. Synthetic materials like plastic are made from crude oil as their source. Now you'll know from your work from organic chemistry that crude oil comes from the ground. It's mined, usually from the sea, and it's this black viscous liquid which contains these hydrocarbons, and these hydrocarbons are what goes into making this plastic. Now their key advantages are the fact that they're quite cheap to make, and also the fact that we can make them really durable. Plastics are really good at surviving. Just think about the times you've gone to the shop and the supermarket's given you a plastic bag, or some of them are giving you a paper bag. The plastic bags often survive the trip home a lot better than a paper bag, and that's a key reason that plastic bags have replaced paper bags. But as you probably know, these plastic materials are having real problems in our environment because of the fact that they are non-biodegradable. This means that they don't break down very well in the environment, and there is a lot of work going in trying to create plastics that are biodegradable. So how do companies decide the product's impact on the environment over its life? Well, they create a life cycle assessment for that product. And a life cycle assessment is broken down into four main parts. That first part is collecting the raw materials from the ground. If it's a synthetic material, that is often crude oil, and this has to be mined. And mining can have terrible impacts on the environment, especially if there is any leaks. Also, if it's a metal, that's often mined, and this can leave toxic byproducts in the environment. The next stage is transporting and manufacturing. Once you've collected them raw materials, they need to all be brought together and put together into a product and then transported where they need to go to. Because we often collect different materials from lots of different places, a lot of carbon is put into the atmosphere, transporting all the different materials from one area to another. All that fuel that's burnt in order to ship and lorry and ferry every piece of material to where it needs to go. The next stage is during the product's life. For example, think about if your product is a car. That's going to have an impact on the environment while you're using it. Not just through the petrol that you burn when you are driving that car, or the diesel when you're driving that car, but also the fact that if you need to replace any parts of that car, whenever it goes in for a service or MOT, all of those go into the life cycle assessment. And then finally, how is that product disposed? Can it be recycled? Is it degradable in the environment? Does it go to landfill? All of these are really important in deciding the impact of that product on the environment. So these life cycle assessments are great in the fact that we can now see the impact of different products on the environment. However, they do have a key disadvantage. And the key disadvantage is that these are often carried out by companies, and they can be quite biased. Just think about if you are trying to sell your product, then you're going to try and glam up its life cycle assessment to make it look like it has a better impact on the environment than maybe it does. One thing that companies can do in order to improve the product's life cycle assessment is look at their disposal after use and emphasizing the importance of recycling of materials. So you probably know what recycling is and you probably do it all the time. But why is it so good for the environment? Well, one, it helps to protect all of our natural reserves, for example, precious metals that we are going to mine from the ground. We're going to have a look at how we extract our metals just a little bit later on. So it helps protect our natural reserves. As well as this, it also means that less of our product goes to landfill. And landfill can be really bad because takes up a lot of space, land that could be used for housing, land that could go back to nature. All of these different uses that we could have for the land, we can't if we fill in it up with landfill. And it often also reduces our energy use in manufacture of the products. It requires a lot of energy to manufacture and extract our products, so reduces our energy use in them scenarios. If you just look at recycled steel, for example, recycled steel uses around 50% less energy to make than normal steel because of the fact that that iron had to be extracted from the ground, and then the manufacture of the steel from the iron that also required lots of energy. So it's around 50% less energy to do that. For this next part of the topic, we're going to look at where we get our water from, and we call our safe drinking water potable water, and this just means safe drinking water. Now, in the UK, we get our water from a few main sources. The first would be groundwater. And what I mean by groundwater is underground reservoirs where it can be found. And we also get it from surface water, and surface water includes lakes and reservoirs. Now, once we've collected our water from one of these sources, then we do a couple of things to it in order to turn it into potable water and make it safe for drinking. The first is we filter that water. And the reason why we filter it is to remove any insoluble substances that might be in there. These can include rocks and sand and leaves or anything that has got into our water source. And then finally, after filtering it, we sterilize the water. We're sterilizing it to remove or kill any harmful microorganisms that might be found inside there. Things like bacteria or parasites. These all might be in that water, and by sterilizing it, it will get rid of these. And we do this by either UV light, ozone, or chlorine. All of these are sterilization methods. We also sometimes add fluoride to our water in the UK, and the reason why we do this is it helps our teeth. It's really good for your teeth. In the UK, we are really lucky because we have lots of groundwater and surface water in which we can use to collect our potable water. However, other countries are not as lucky and they have to use salt water as their source for their potable water. And they have to treat their water a little bit differently because obviously we need to remove that salt in order to make it safe to drink. And there's a few ways that you can do this. There is one way which is distillation, and we know what distillation is from other topics. We have to heat up our salt water, it will evaporate, and it will actually create pure water. Now, once you've got this pure water, you will actually need to add minerals to it because pure water is not good to drink in its pure form. You need some minerals in there to make it a little bit hard, things like fluoride or the metal ions. These are actually good for you. So distillation requires lots of energy to do, and it also produces pure water, which we don't really want. We want potable water, so we have to treat it further. And the other way of collecting our water is reverse osmosis. And just like distillation, these both require lots of energy, and these make pure water. And pure water is not what we are after. When we're doing this, we're after potable water, safe drinking water. So we actually have to add minerals to it after these processes. You may have done a practical in the lab where you've done a distillation on salt water, and just remember you could always test that you had pure water because of the fact it would have a boiling point of 100 degrees, and you could also test that it had no sodium ions in there because you could do a flame test on it and it wouldn't produce a yellow flame like sodium would. As well as making safe potable water, we're also going to look at what we do with our dirty water and treating our wastewater. Now, wastewater can come from a variety of sources. It can come from when we shower, it can come from washing our clothes, it can come from when we flush our toilets, and it can also come from agriculture. So as you can imagine, we have a lot of wastewater to process, and it always takes place with these key steps. The first step being the water is screened, and this screening is a really important process. It removes all the really large insoluble objects that are in that wastewater. Now, all of this waste often gets sent to landfill. So it's things like tissue paper, cotton buds, all of that stuff. And that's why it's always advised not to put anything too large into your toilet when you flush or down the drain. It's because it can actually clog up the screening and it can damage the equipment there. So after the water has been screened, it gets sent to what is called a primary settlement tank. Now, what happens in the primary settlement tank is the water is slowed down. And what happens is the large insolubles sink to the bottom, and what happens with all of these, so things like poo, it goes to the bottom of the primary settlement tank and it gets taken away. Now, we actually use some of this, we turn it into fertilizer, so it's a useful byproduct of this process, is that in here we collect it and we use it for fertilizer. Now, what we do is we actually carry out what's called anaerobic digestion in this stage. What we do is we put in there, bacteria, and we starve it of oxygen, and it helps break it down and create this fertilizer, which then we use for crops. The next stage is we will pass the water through bacteria treatment, and what happens in this is basically we put in good bacteria that gets rid of any of the bad bacteria, and this happens through aerobic digestion. So last time we starved the bacteria of oxygen in the anaerobic digestion for the solid material. This time we actually pump in oxygen, and the good bacteria gets rid of all of the bad bacteria that is inside there. And then finally, the water is filtered, and this gets rid of any of the last of any of the solids. It's passed through fine filter, which is sand usually, and this is the last step before it's released into the river. Another resource we are going to look at is extracting metals. Now, this is a higher tier only topic, so if you are on foundation tier, on combined science, well done, this is the end of the video for you. If you're higher tier combined science, you have a little bit to go, and if you're triple science, you have quite a bit to go. Now, if we are extracting copper or iron from a high grade ore, this is quite simple. Now, what I'm referring to when I'm talking about an ore, I am referring to a rock containing metal. And when I'm saying it's high grade, I mean that it's containing a lot of that metal. And I say that it's quite simple to extract from a high grade ore because we can use traditional techniques. First, the metal is mined. And then secondly, what we can do is we can extract it using carbon. Now, this technique is called smelting, and it requires lots of energy and is incredibly bad for the environment. If I just draw out a word equation here for what's going on, if I've got copper oxide and I'm adding it to carbon, I get a displacement reaction because carbon is more reactive than copper, and I will make carbon dioxide and I will make my metal, which is copper. So obviously you know that carbon dioxide is a greenhouse gas, and being emitted to the atmosphere is obviously not going to be good for the environment. But on top of this, you also have a few more negatives of this process. For one, these high grade ores, they are running out. These metals are a finite resource, and high grade ores are becoming harder to find. As well as this, the mining sites can also produce environmental problems. Just think, what was there before the mine was there? That could have been a habitat, that could have been a rainforest, and what's left behind? Sometimes you end up with toxic byproducts that are formed because you've got areas of metal being exposed to water, and you can end up with these pits which are full of toxic chemicals. So let's have a look at some other ways of extracting. We'll just focus on copper here from low grade ores, so rocks containing metals but not in so high amount. And these techniques are generally seen as a more clean and sustainable way of collecting these metals. But as you're going to find out, they do have a couple of downsides as well. So the first one we are going to look at is phytomining. And what phytomining involves is growing a plant on the low-grade ore, and what happens is over time the roots take up the metal, and because of this the plant will now contain that metal. And what we then do is we burn the plant, and the metal will then be contained in the ash. And then finally what we do is we add an acid to the ash, and then we can carry out an electrolysis and we can collect our metal from that solution. Now, as you can imagine, this is an incredibly long process to carry out. Plants can take a long time to grow, and the amount of metal that you create is often a lot less than if you are doing it off a high grade ore. So it's quite a small scale thing that you are doing. However, this is a pretty carbon neutral technique. As the plant is growing, obviously it's taking carbon out of the atmosphere, and then we are burning the plant, obviously, to collect that metal. So let's have a look at another technique, and that is bioleaching. And bioleaching essentially uses bacteria in order to extract the metal from the ore. And just like phytomining, it does take quite a long time, but what you end up with after placing this bacteria on there is you end up with a solution called a leachate solution. And just like with last time, this leachate solution needs to have an electrolysis carried out of it, and then you can collect your metal from that solution that's formed. It does have a couple of different problems with it. It produces sometimes toxic side effects, some toxic byproducts, from carrying it out. And as well as phytomining, it does take a long time as well. Now, if you are doing combined science, you are finished. Well done for sticking along. And if you're doing triple science, you just have a little bit more to go in the video. Now, we've had a look at how to extract a metal, but let's now have a look at altering some of the properties of metals and what we can do with that. So if we just look at our pure metal over here, metals have the structure of having positive ions surrounded by delocalized electrons. And these positive ions are in layers, and this is what makes metals very malleable. The layers can slide over one another, and it also, because of the fact they've got these delocalized electrons that can move freely through the structure, they make them really good conductors of electricity and heat as well. What happens if I want to alter the conditions of my metal to make it maybe even harder, to make it a little bit more resistant to corrosion? Well, what I can do is I can create an alloy, and an alloy is a metal containing two or more metallic elements. Now, if we look at this alloy shown in the image, you can see that I have two different atoms present here. So that means I've got two different types of element in there. And basically that layer structure has now been disrupted. So this makes the layers much harder to slide over. So because the layers are harder to slide over, it makes them much harder. And you need to know some examples of alloys. So we have steel, which is a mixture of iron and carbon, and you can actually change the ratio of iron to carbon atoms to change the properties even further. You also need to know al-nico, which in the name is aluminium, nickel, and also cobalt. Due to the fact it contains two magnetic elements, this is also a strong magnet as well. Another example is brass, which is zinc and copper. Now, metals will react with oxygen in the air, and this is an oxidation reaction, and it's called corrosion. You probably know about one specific type of corrosion reaction, which is called rusting. And rusting is a specific type of corrosion. It happens in iron or steel. And you can actually carry out a practical to investigate the conditions required in order for rusting to occur using some iron nails. And here I'm going to show you how to carry that out. Now, in this first test tube, you have some iron nails, and to see the effect of water and oxygen on whether you get these nails to rust, what you can do is in one of the test tubes, put some water and nothing else on top of there, so that this one will be exposed to water and oxygen. Now, in this one, you should expect to see lots of rusting take place because of the fact that water and oxygen are needed for corrosion to occur. In the second test tube, what you can do to see whether it is water and oxygen required is in this one, you can put some water, and on top of the water, you can put a thin layer of oil. Now, the oil is going to mean that no oxygen can get to them nails. So this one is just seeing the effect of water. And on this one, you should see maybe a little bit of rust, but a lot less because oxygen is required in order for rusting to occur. And in the last one, what you're going to do is you're going to place some calcium chloride chips in there, and you're also going to put a bit of cotton wool over the top of your test tube. So what this calcium chloride is going to do is it's going to absorb any of the water in there, so that you're going to get no water or oxygen. And in this one, we should see that we do not get any rusting occurring. Now, there are ways to prevent corrosion because obviously you do not want your metal to corrode away over time. So there's three techniques we're going to look at. The first one is the sacrificial method, and what you do is you place a reactive metal around the outside of whatever you're trying to protect. Now, a good example of this is galvanizing, and in galvanizing they place zinc around the metal, and zinc is reactive, so this will react with the oxygen in the air and this will corrode, and leaving the metal underneath to be safe. The next method is the physical barrier method, which prevents oxygen or water from getting towards your metal, and this can be done using things like plastic or painting your metal, and all this is doing is preventing water from getting to the surface and preventing oxygen from getting to the surface. And the last technique is electroplating. What you do with this is you place a very unreactive metal around the outside, for example, silver, and what this does is it protects the metal underneath that might be more reactive, that would react with the oxygen and water. Now we've investigated metals, the next material to investigate is polymers. And polymers are incredibly interesting, and there are two main types of polymers that you need to know about. And the first one is thermo-softening polymers. And the key difference between the two of them is that the thermo-softening, these are not heat resistant. These if you heat them up, they can be remolded or reshaped. And they are not heat resistant. These are really useful for things that can be recycled, and also for them one-use plastics. The other type of polymer are called thermosetting polymers, and the key difference between these thermosetting and thermosoftening polymers is the thermosetting polymers have links between their chains. These are called crosslinks. And these are strong covalent bonds that hold the layers together. And these make these polymers incredibly heat resistant and also much stronger. These are often used in building materials. Now, just comparing them strong covalent bonds that are in those thermosetting polymers to thermosoftening polymers, the key thing is that these do not have the crosslinks in the thermosoftening, and they only have weak intermolecular forces holding them layers together, and that's why they are not as heat resistant. We're now going to look at a couple of different types of materials. We're going to focus first on ceramics. And ceramics are made by putting clay into a furnace and heating it up to a really high temperature. In its pure form, clay, when you add water to it, it's really easy to mold. But when you heat it up in this furnace, what it does is it creates a huge lattice structure with lots of ionic and covalent bonds. And this makes ceramic materials incredibly heat resistant, which makes them perfect to be used in cooking equipment and plates and things like that. Also, it means that they are quite brittle. This means that they shatter upon hard impact and they can be stuck together and all the pieces will fit back together. Another type of material are called composites, and these are made when you combine two or more materials to produce something with improved properties. And composites are usually comprised of two materials, one being the reinforcement and the other being the matrix, which binds the reinforcement together. Now, this is more easy to understand if you have an example. And a good example is reinforced concrete. Now, in reinforced concrete, the matrix is the concrete that binds everything together, and the reinforcement will be steel, and that is why it's really, really strong. Another example is fiberglass, and fiberglass contains a glass reinforcement with a matrix of a polymer which glues it together. The last bit of the video, we're going to focus on fertilizers, and the first thing to focus on is how to make ammonia, because ammonia is a key component to many of the fertilizers that we're going to look at. So the way to make ammonia is by a process called the Haber process, and in this I react nitrogen with hydrogen to make ammonia. And this is a reversible reaction shown by my reversible arrows. And it's really important to remember that the forward reaction for the Haber process is exothermic and the backwards reaction is endothermic. So when creating my ammonia, I'm trying to balance the fact that I want to make as much ammonia as possible in as fewer time as possible. So I have to have compromises. And this is taking into account everything that we've learned about Le Chatelier's principle and also what we know about rates of reaction. So you need to remember the conditions for this reaction and know why we choose each condition. And the first condition you need to know about is the temperature the reaction is carried out at. And the reaction takes place at 450 degrees C. And the reason why we choose this temperature for the Haber process is because of the fact if I used any higher temperature, then the yield for my reaction would be too low. So if I use a lower temperature, I increase the yield of ammonia. The reason being it's exothermic in the forwards direction and endothermic in the backwards direction. So higher temperatures have a smaller yield of ammonia. Just think, if I increase the temperature, the endothermic reaction would be favoured, shifting my reaction backwards, remaking my nitrogen and hydrogen, which is not what I want to do. Now, the reason why I still choose 450 degrees C, and it might sound quite high to you, is because of the fact that if I chose a lower temperature, these reactions happen very slowly. So a lower temperature would result in too slow of a reaction. So it's a compromise between rate and yield. The other thing you need to know is the pressure that this reaction is carried out at, and it takes place at 200 atmospheres of pressure. Now, the reason we choose this is because I have 4 moles of gas on this side of my equation and 2 moles of gas on this side of my equation. So I want to have a high pressure because then I will increase my yield. So high pressures increases the yield of ammonia. Because when I increase the pressure, the reaction is going to try and decrease the pressure, and it will favour the forwards reaction, shifting my reaction forwards to produce the lower moles of gas, which will occupy less space, ultimately reducing the pressure and reaction. Remember Le Chatelier's principle, a reaction will always try and counteract a change if it's in equilibrium. So high pressures increase the yield of ammonia. So why don't I just keep going up? Why don't I do 700 atmospheres of pressure? Well, really high pressures are dangerous and expensive because you've got hydrogen in there, which is highly flammable. If I increase the pressure too high, then I could get explosions happening. And also, they're really expensive to create. It requires lots of energy to create pressures much higher than 200 atmosphere pressure. You also need to know that this reaction has an ion catalyst. Now, what this is doing, it's lowering the activation energy. Remember this from rates of reaction. So therefore, you need milder reaction conditions. Remember, it does nothing to affect the yield of ammonia. It's only going to mean that you need milder reaction conditions, which will make it cheaper and require less energy for the reaction. But in industry, what does this reaction actually look like? Well, down here, I'm putting in my 2 reactants, and let's just circle this. This is the first stage. You're going to add nitrogen, which comes from the air. That's a nice and cheap reactant to get, isn't it? Remember that the air is 78% nitrogen, so it's really easy to get nitrogen, but the hydrogen is collected through electrolysis of water, or it's collected from methane. So this reactant can it does require a lot of energy to get the reactant in the first place. Also, storing hydrogen can be a little bit dangerous as well, so that's another problem of this reaction. So once I've collected my two reactants, I send them into my reaction chamber. And inside this reaction chamber, I have the conditions that were on the last slide. Remember, 450 degrees C and 200 atmosphere pressure. And the reaction takes place here. You've got that reversible reaction, nitrogen plus hydrogen, and it's making my ammonia. And what I then do is I cool it down in what's called a condenser. And this is going to separate any unreacted nitrogen and hydrogen from my ammonia. Ammonia has a lower boiling point. And because it has a lower boiling point, this means it condenses at a lower temperature and can be separated from nitrogen and hydrogen. But what do I do with my unreacted nitrogen and hydrogen? Well, what I do is I recycle it back round. As a consequence, I don't make any waste products from this reaction. All that nitrogen and hydrogen that's unreacted, I just send back round for it to react again. Also, removing my ammonia from my reaction chamber, I'm shifting my equilibrium further forwards, because if I'm removing my ammonia as it's forming, my reaction is going to shift to try and make more of it, thus increasing my yield even further. Now, the ammonia that was collected from the harbour process can now be used as a fertiliser, and fertilisers are incredibly important to farmers. They help the farmer create bigger crops, and therefore they can sell them for more money, makes it more economically viable to farm, and increases the economic gain for the farmer. However, the ammonia connected from the harbour process is in a liquid form. So what you need to do is you need to react it with an acid, and you need to create an ammonium salt. So there's a few acids that you could choose. You could react ammonia with sulfuric acid, and this would make ammonium sulfate. When you've reacted it with the acid, you must crystallize it after, remember, as well, to make it get rid of any unreacted sulfuric acid. You could also react ammonia with phosphoric acid, and this would make ammonium phosphate salt. Or alternatively, you could use nitric acid, and this would make ammonium nitrate. Now, you could carry out this reaction in a lab if you wanted, and maybe you actually did this with your teachers by doing a titration using the ammonia as a base and using the acid to react together. And this would just be a simple titration, and then use a crystallizing dish, and you could then collect your fertilizer salt. Now, there is some benefits of carrying it out in the lab in the fact that it's quite safe. You have mild reaction conditions. However, it takes an incredibly long time to just wait for something to crystallize. So this takes a long time, and you can only make it in quite small amounts. As a consequence, these reactions are carried out on an industrial scale, and what the difference is the fact that we now create a much greater yield in much less time. But to do this, it comes at greater risk. They use not mild reaction conditions, they use extreme reaction conditions, which can increase the danger. They use higher concentrations. Might be asked in an exam to compare the production of fertilizer in a lab compared to the industrial production, and these are things that you could use in your comparison. As well as nitrogen, crops also need other minerals in the soil in order to grow. And the key elements are nitrogen, phosphorus, and potassium. So we call these fertilizers NPK fertilizers. And to get a fertilizer containing phosphorus, what we actually mine is something called phosphate rock. And the key thing to know about phosphate rock is it's insoluble. It will not dissolve into the ground. So you need to treat it in order to make it soluble so that it can be spread on the fields. And the way we do that is we react different acids with our phosphate rock. And if we look at the first acid, phosphate rock and nitric acid, we make phosphoric acid. And you just need to remember these three reactions. And you also make calcium nitrate. Phosphate rock and sulfuric acid make single superphosphate. And phosphate rock plus phosphoric acid makes triple superphosphate. And you just need to remember these and remember how to turn phosphate rock from insoluble to something soluble by doing either one of these three reactions. Now that is absolutely everything for this unit. I know it was a long video, but well done if you stuck around to the end, and best of luck with everything with your exams and your GCSEs.